Hello. Today I will be presenting ERUPT Efficient Rendering with Unposed Patch Transformer. Our work focuses on the fundamental problem of 3D scene reconstruction applied for novel view synthesis. Given a limited set of unposed images, ERUPT recovers a queryable 3D scene representation where frames can be rendered by providing query camera poses. In this paper, we address the key challenge of efficiently encoding and decoding a scene representation to enable large-scale training on real and synthetic datasets. Recent advances in 3D scene representation have shown impressive capability in rendering complex environments. When provided dense imagery and precise camera pose, techniques like NeRF and Gaussian Splatting provide high-quality output. However, performance degrades when images are sparse or camera pose is noisy, which is a common case for most real-world data. Additionally, methods like NeRF and Gaussian Splatting are scene-specific, and knowledge learned from one dataset cannot be easily applied to another. Latent scene representation methods like RUST or SRT look to address this limitation by training a generalized model across diverse datasets. However, existing latent scene representation models still require precise camera metadata to learn a fully posable representation and rely on expensive pixel-wise decoding, making them computationally expensive and difficult to scale. To address these limitations, ERUPT is specifically designed to learn from both posed and unposed inputs. First, visual features from the input and target images are extracted by a pre-trained Dino V2 network, which are added to a reference frame encoding and positional encoding. Next, the token sequence is processed by a scene transformer, which alternates token mixing within and between images to produce a latent scene representation and camera pose estimate for each image. ERUPT also provides camera pose estimates for each image. For cases where ground truth camera pose is available, it is inserted at this stage in place of the estimated pose. To improve computational efficiency, we query the scene representation using patch ray tokens, which represent 8 by 8 pixel patches in the image. We implement two patch ray decoders, one for decoding the scene representation to pixel output using an L2 loss, and another to generate image tokens, which are contrastively aligned using an auxiliary perceptual loss. As an optional step, we show that the tokens generated by ERUPT can be used as conditioning to fine-tune a stable diffusion model, further improving perceptual quality of the generated images. Our unique patch-based decoding allows us to recover 64 pixels per query instead of 1 pixel per query using pixel ray tokens, which drastically improves performance. This important design choice allows ERUPT to be efficiently trained on large datasets to improve generalization and robustness. We trained ERUPT using the multi-ShapeNet dataset, containing 1 million synthetic images of ShapeNet objects in virtual environments with perfect camera pose. We show 2 example scenes with 5 example input and target views each. Additionally, to demonstrate ERUPT on real-world data, we collected the MSVS 1M dataset containing images gathered from Mapillary's API. The dataset contains a variety of challenging in-the-wild characteristics, including transient objects and camera pose inaccuracy, which we provide for download on Hugging Face. We experimented with several model variations of ERUPT. Our baseline model was trained using a Dino V2 backbone at 224 by 224 resolution. In our ERUPT plus GAN model, we added an adversarial loss to the image decoder, and in the ERUPT plus Stable Diffusion variant, we fine-tuned Stable Diffusion version 2.1, using tokens generated by ERUPT as a conditioning signal. We also experimented with fine-tuning the backbone network to better align to the 3D scene reconstruction task in the LoRa setup. We report results on the multi-ShapeNet dataset for several variants of ERUPT. We also note whether models require posed or unposed images. Using the ERUPT plus LoRa model, ERUPT surpasses existing methods, even those trained with fully posed inputs. The GAN and Stable Diffusion model variants further improve perceptual quality as seen in the lower L-PIP scores. Views generated by our models are generally consistent from frame to frame as seen in the animation of rendered images for these 2 scenes. Using the ERUPT plus Stable Diffusion model variant yields some inconsistency between frames as expected, due to the nature of diffusion-based probabilistic sampling. When ERUPT is trained on the MSVS 1M dataset, it is subject to the in-the-wild perturbations present in the Mapillary data and is still capable of reasonable scene reconstruction, even in this challenging case. In summary, we presented ERUPT, a latent view synthesis model which improves rendering efficiency and reduces reliance on posed inputs, enabling novel view synthesis for images with missing or noisy metadata. We achieved state-of-the-art performance on benchmark data and demonstrated the effectiveness of ERUPT on a new dataset for real-world view synthesis.
Thank you.